Welcome to Fun with Science, Engineering, and Technology. My name is Mr. Ross. My assistants today are Bernard and David. And what we're going to do today is, in the science, everybody always has to weigh something. And we have all kinds of different scales for weighing things, find out how much things weigh. Right? So that's what we're going to do today. We're going to go back and take all the scales that you've used in the classroom. We're going to talk a little bit about them, and then we're going to try to figure out how some of them work. Right? So, the very first ones, one of the very first ones that used probably was this. You remember what this is called? It's a spring scale, right? And the reason it's called a spring scale is because back here in the back there's a little spring. If you look in the back of it, right? And what you do is you can hang the scale up like this, like it's hanging on my finger, and then you can put a weight on it, right? And the more weight you put on it, right, the more it stretches that spring and moves the little pointer down on the scale and gives you a reading. Now, what's the scale read on this one?
Grams and newtons.
It reads grams and newtons. It reads grams on one side and newtons on the other side. All right? Wonder why we did that. All right, they both start out at 0. The gram side ends up reading 5,000 on this particular scale, and the newtons are
50.
50, right? So how many grams are there in a newton?
10? No,
100.
100 grams in a newton. All right, and the reason we have two scales, basically, is sometimes when some of the formulas we use when we're going to do some calculations in the science for forces and so forth, the formulas are set up to use newtons, right? Use 100 grams, right? And at other times, right, we use the plain gram scale. No. If sometimes it looks like that, it's off when there's nothing hanging on it, the little pointer doesn't read on 0, right? So we have to calibrate it. And this particular one is calibrated by moving this up and down, which actually moves the scale up and down till where the pointer is at 0 to start with. Right? So that's a spring scale. And it's sort of accurate if you don't want a real accurate reading, right? And the more you use it, right, guess what happens to the spring back here?
It gets weird out and stuff.
It gets wore out, it gets stretched a little bit, and then it does away with the accuracy on that spring scale. So that's one of those kinds of scales we use, right? The more weight, the more the spring is stretched. Right. What about this one?
How about it? It looks
Same
like a
spring
spring
scale?
scale.
It looks like a spring scale. It is, right? It's a different kind, all right? And you can see in here, you can see the spring, right? And here's the little place where you can hang the weight, move it up and down, and guess how it's calibrated? What's it on that side?
Grams.
Grams and
Newtons.
newtons, right? So this particular scale works just like that one, right? They look a little different, right? Now, these usually, when you see these in the classroom, right, they come in different colors, right? And what the different colors indicate is the maximum number of grams or newtons that it weighs, right? If you want this thing to weigh more, what you need to do is you need to make that spring a little bit heavier, right? Make it a little bit stronger, so that if you make it stronger, then it takes more weight to pull this down, right?
Yep.
I wonder how you adjust this one. It's reading pretty close to 0, huh?
Yeah, I think it will.
But how would you do it?
Something up here.
Something up here, right? All right, right up here on the top of it, there's a little nut that we can turn, right? And what's happening to the indicator now?
It's going
It's
up
moving.
to
It's
0.
going up, right? And what I'm doing on this one, where when I adjusted it, calibrated it for 0, I actually moved the scale up and down. On this one, right, which is a little bit better, is I take this nut and I turn it, and there's some threads in there, a little screw, and what it's doing is actually stretching the spring a little bit more. Right? I turn it the other way, and I reduce the tension on the spring, and the scale should go back down to 0. Okay? And we always want to start out with 0. Again, what happens to this one after a period of time?
The spring wears down.
This spring gets stretched, right? because a lot of the students, what did you do with this when you got this one, when you used this one in the 6th grade, I believe? What did you do with this one? Very first thing you did with it?
I don't know, stretch it.
Huh?
Stretch it.
You went and stretched it,
Stretched
right?
it, yeah.
Right? And after the students do that enough times, guess what?
It was.
It becomes
spends-
stretched out.
Yeah, and then you come along and you try to make a real scientific measurement,
It
and the spring
becomes-
is all stretched, and your buddy stretched the spring out so you don't get the right kind of reading. Right. So those are 2 scales, 2 spring scales. Look a little bit different, but they work basically the same way by the tension on that spring. All right, let's put those down over here out of the way. Did you ever use that one?
Yeah.
I made
Yeah.
one in the 4th grade, but
You use one in that back down in the 4th grade? Yeah, the 5th, 4th grades, you usually use that one. And that one is, what would you call that thing?
a balance
A
beam.
balance beam.
It's a balance, right? But what is it really? Something you learned in the
A
6th grade.
seesaw also.
It's a seesaw, teeter-totter, right? But what else is it? I know that Mr. Rattel,
Talked about
you
this
had 3
one.
classes of these things.
Um,
Class 1, Class 2, and Class 3.
It's
Think back a little bit.
class 1 scale.
Lever.
Lever, yeah.
It's a lever, right?
Oh,
It's,
yeah.
it's a lever,
Yeah,
right?
that's
You got you got the fulcrum here, right? And then you got the lever arms, right?
Yeah.
So it's basically a lever, right? And right now it happens to be balanced up, right? The 2 arms are equal distance from the fulcrum, right? The weight is the same on both sides of it, so it's going to sit there once we quit rocking around a little bit, and it's going to balance up and be 0. Right? If you look here, there's a little mark going down here, lines up with the mark here. You got one on this side too. It's one on both sides, right? Right. So now, and what you did when you used that, you had a set of weights, right? They were all calibrated. You
It's
knew
like
that
1
one was
kg,
1
yeah.
gram, one was, 2 grams, whatever it was, and you put something in one side that you didn't know what the weight was,
Yeah.
right? And then you put the weights on the other side until you got it all balanced up.
Yeah.
Yeah, we don't have any weights today, okay? But I have a bunch of my lunch money. Right, I have a bunch of coins. I have some quarters. I have some pennies. I have some nickels, right? Let's put a nickel on this side, right? And what we want to do, if you look at it right here, there's an X here and there's an X here, right? And what we want to do is we want to try to put our weights and our load right on that X in the center of it, because if we put it too far over this way,
It'll be way more on
it'll
this
be,
one.
yeah, this arm will be a little bit longer than the other. So we want to put my nickel right in there, right? Now then,
Pennies.
I'll give you some pennies. I want to see if you can balance it up now.
Not too much.
Here, how many you got in there?
I
2.
think
2?
that's too much. I think that's
Now
too
the
much.
pennies way.
No, two's too
much,
many? Oh,
yeah.
3's too
Three's too
many?
many.
Pick
Yeah,
one
it's
out.
2.
It's 2.
It's 2.
Two.
And
Right.
everything is
So 2 pennies balances out. So 2 pennies must equal
1 dime.
one
Nickel.
nickel.
Yeah.
You think you're going to get away with that at the store, going and hand them 2 pennies and say, hey, this is a nickel, I want a nickel candy bar. Well, candy bars aren't a nickel anymore. They used to be when I was a kid, but not anymore, right? So you can't trade 2 pennies for a nickel, can you?
No.
Nobody's going to go for that. Right, the reason, but the reason that balances out is our coins all have
Mass.
a mass, and they have a weight, right? And what's happening, a penny or a cent is 2.5 grams.
Huh.
All right?
I don't know.
It weighs 2.5 grams. A nickel, which is the one to remember, right, because we can use it. Nickel is 5 cents, and it's 5 grams. So 2 pennies, right, 2 times 2.5 is 5
5
grams,
grams.
right? A dime is 2.2868 grams, and a quarter is 5.67 grams, right? So if we can remember all those, we have our own little set of weights calibrated that we carry around in our pocket. This nickel always weighs,
So
5
5
grams.
grams.
this penny always weighs
2 and a half.
2.5.
2.5, right? 2.5. So this weighs half of the nickel, so we can use those as our standard weights. All right. Now, why does it balance out?
Because they have
The
equal mass.
weights, yeah.
They have equal masses,
And the support, they have like equal lengths from
Okay.
the middle.
right? But what if I take this one off over here?
Yeah, this one would be really nice.
Okay. Why did it go down like that?
Because
Because
this
it
has
has
more
more-
weight
this-
on the
this one
side.
has
Okay,
more
but what made
mass.
it go down?
For the
The-
weight of the pennies.
What's weight?
Um, The grams?
line-
Yeah, but what is it?
A force.
It's a force, right? It's caused by a force.
Like gravity or something?
Yeah.
Like, aha, you said the magic word, like gravity. So if I have the same mass, basically, over there as I have over here, right? Gravity's pulling down on this with a force of 5 grams.
Grams.
Those 2 pennies over there, gravity is pulling down with a force of
5
Five
grams.
5 grams total. So it balances out, right? So we've got them balanced. If it pulls down with more force on one side, if we have more mass over here,
It will be
Yeah, we
unbalanced.
look
it'd be unbalanced, it would come down this way. In other words, if I take whatever to put two nickels in there,
You need
Right.
2 more.
it's unbalanced. All right, so that's a little scale. It's balanced up. Just like my Snoopy and my little wood stocks up here, right?
Yeah.
I've got they're sitting out on one side of the lever and this weight's on the other side. And if we get them all adjusted right, right, it balances out. What if I were to move the wood stocks back closer to the
This one would be way heavier.
Hmm?
This one would be it go
All
down.
right, this one will go down because what we're doing, we're shortening the
Length.
length of the lever. Right. Right. So if we were to move my little wood stocks back, right, then it would become unbalanced. All right. So. All right. So, all right, give me back my lunch money. Okay, now, Bernard, will you take that and put it down on the floor? Let's get rid of that one. For the time being. Okay. Now then,
Triple balance.
you know what this is called?
A triple balance beam.
A triple balance beam or triple beam balance. And it's
Yeah.
called triple beam because
It has 3.
3.
it has 3 beams out here. Right. That, believe it or not, works just exactly like the one we just took down. Right?
Mm-hmm.
It's a lever. There's a fulcrum down in here, right? This is on one side of the lever, right? And this is one side of the lever, right? On one side of the fulcrum, and this is on the other side. Now, what we do is we can put whatever we're going to weigh there, right? What happened to it?
It goes down because
It went down, right? Because we've unbalanced the lever,
Yeah.
right? So now then, what we have 3 little weights over here.
Hundreds, tens, and ones.
ones.
Hundreds, tens, and ones, right. So this hundreds, if we take and we move it, right, it has little notches, right? And we move it all the way over there, what is it? What do it read? What does it read?
100.
500 grams.
500 grams, right? And so each one of these little notches is what?
100 grams.
Each one represents 100 grams, right? So, now then, this one is the next one up, and if I move it one notch, what is it?
10 grams.
10,
20,
20, 30.
30.
And if I move it all the way over to the end,
50.
100 grams.
it's 100 grams. So, if I move this all the way across to the end, it's 100 grams. If I move this just one,
It's
what?
200 grams.
okay, so now it's 200. But moving this distance like this and moving this one just this distance is the same.
Yep.
Right? This is 100 grams, this is 100 grams. All right. What about this one down here?
1 gram.
Right, just by 1.
4.
So if I move it all the way over to the end, what have I got?
10 grams.
10 grams, which is
The
the same as one step here, right?
Yep.
Yeah.
Okay. So you want to,
Figure out the.
yeah,
what
figure out what that weighs.
Yeah, it's too much. It's too much.
So just move this.
Yes, yeah. The hell? Too much. Go back a little bit.
Wait, 100 here.
Oops.
So-
Yeah. Hold on. That means if it's over 100.
Wait, get back to this one. And
Yeah.
move in.
100. Yeah. Then start by 10.
200.
That's
Weighs too much. So
go 100. 100, then 10, 20, then too much. 120, 10.
it's too much. So
Right there.
yeah, it's 104
104.
grams.
104 grams?
Yeah.
Okay, so you had to do a little bit of fiddling around to get it. Okay, here's the secret to doing this. Right? Take the big one first.
Yep.
Right? You move it over one notch. Right? It didn't go down, did it?
No.
Right? I move it over 2 notches. What happened?
It
only
went down.
It went down.
So
So
we
what
move
I
it
want to
back.
do is I move it back 1. Right? It's back up. Now then I start moving the next heavy one. Right? I went over 1 notch. It went down.
Yep.
Right? So that's too far, so I need to move it back 1. Right? You want to make sure it's in the notch, right? You don't want to get it halfway in between, right? Because it's not in the right spot. And then you start moving.
The one.
Right?
Half over.
No
Right.
problem.
We're pretty close?
Mm-hmm.
Okay. Now, what was it again?
100 and
It's 106.
106 right now.
106 grams?
Yeah.
Right. Now, how do we adjust this one? On these spring scales, we adjusted them by either moving the scale, right? Right, or by adjusting this little screw up on top and stretching the spring. How do we adjust that one?
Return everything to the end.
We move
Move everything to the end, okay, and it should read 0. What if it doesn't?
You
Oh.
wait for it. It should need 0.
How do you adjust it?
by moving these weights.
Okay, but they're
All the
over,
way
we
over.
can't get them back here any further unless say that it was down below 0. How do you adjust it?
How would you adjust it?
Well, one of the things I could do is I could start putting a little weight on here, right?
Yeah.
Or what I need to do, if I could do it, if I could extend the length of the lever arm on this side of the fulcrum, then I can make it go up and down. If I can change that lever arm, all right, or change the weight just a little bit. Right, there's a way to do that. And it's right down here. Right, there's a little adjustment thing here.
Oh,
Mhm.
never saw
Right,
that.
you can turn this, that's what that's for, right? And what you do is you set it up, right, because one couple things happen is if the table wasn't quite level or something, it might not read 0, right? So then you need to set it up and you need to adjust it to where with nothing on it, it reads 0. Okay? So again, this is just like
The
that
balance beam.
blue balanced scale we had. Gravity is pulling the weight down here, right? Forcing this side of the lever down. The gravity is pulling these weights down, and you can adjust to where they are on the lever arm, right? Until you get it balanced up. So, now, another interesting thing about that. If you notice, when we move a weight, we don't move it too far. What happens to that arm?
It goes
It-
up or
It goes
down.
up and down, right?
Yeah.
Just sort of like
That one.
that one, right? Because I touched it, and it sits there, and it goes up and down, it goes up and down, right? And it goes up and down for quite a while, right? Which could get a little bit aggravating when you're trying to measure your thing. You move the little 1 gram one, right? You move it 1/10 of a gram, and it sits there and it goes up and down, up and down. You have to wait for it to, settle out.
Yeah.
So, there's a way to make it settle out, right, on that. And it all has to do with plumbing. Not really. I have 2 pieces of tubing, all right? I have a piece of copper tubing, and I have a piece of PVC, plastic tubing, right?
Yeah.
And they're both the same size, believe it or not. They're both half-inch diameter on the inside, right? The plastic one looks a little bit fatter because the
Yeah.
plastic's thicker, right? Now, what do we know about these two pieces of tubing?
Same height.
They're the same length,
Yeah.
right? And if I were to take, what's that?
Bowl,
A
nut.
nut, it's a nut, right? Just like the three of us, right? So, what I want you to do, David, come over here, right, around the side. Bernard, you don't have to get, no, don't get around here, right here. I just want you to hold your hand down there. I'm gonna drop the nut down,
Yep, got it.
right, it come right out, right?
Yeah.
You wanna do it again with the plastic one? Right, it fell right down,
Yeah.
that little nut. Is that
And
fascinating? Is that scientific? Bernard, here, you hold that for a moment. Over here, in my little pill bottle, I have. Why do you think all those things are stuck to the side of the plastic bottle?
magnet inside.
There's a magnet inside there, right? Right? And if we look at it, what I have here are two little magnets, right?
It can go through your body too.
Hmm? What's
Cause
happening?
The
Huh?
magnet's
It's
moving.
pulling-
The magnet's moving, right? Because I have two of them. I got this magnet and I got this one, right? And I can make it right through my hand. So these are pretty powerful magnets. See if you can get them apart. Huh?
Yeah.
It's a little tough, right?
Yeah.
For such little itty bitty magnets. Now, so this is going to stick to paper clips and steel and things like that. Will it stick to this plastic?
No.
Oh,
No, it's because it's not magnetic. How about this copper?
No.
Don't stick to the copper, right?
Yeah.
David, come on. All right, I'm going to drop it in the plastic thing.
Yeah.
Right, come right down, right?
Yeah.
Just like the nut. Okay, now this time I'm going to drop it in the copper one. Well, what are you waiting for? Its show's going to be over by the time you get it.
It's inside there.
Huh?
It got it got attracted to the inside of that.
But it doesn't stick.
The inside has a different maybe.
No, the inside's copper too. Look down in there. Do you see anything different on the inside? It's
No.
copper, huh?
No.
Right? Let's try that again. Let's try that again. Why is it? Let's move your hand down a little bit. What happened?
It somehow got attracted into
It
that.
somehow got attracted in there, didn't it, huh?
Yeah.
Look, the plastic one, let's do it in the plastic again. Right out.
Yep.
Somehow it got attracted in there. So what's the difference between these two things? They're both, neither one of them are magnetic, right? That won't stick to it.
the copper's a metal.
Copper's metal,
Yeah.
and that was plastic. Metal is what? Metal is a good conductor of electricity, right?
Yeah.
All the wires that bring the electricity into these lights are made out of copper.
Yeah.
Okay? Plastic is what they call an insulator. Right? Now, one of the ways that we generate electricity is if we were to take a piece of wire, run it up and down through this magnetic field, we generate electricity, right?
Yeah.
You knew that, didn't you? So now then, what if I hold a piece of wire steady and I go like this with a magnet?
A piece of what?
Take the wire and I hold it steady, and I move the magnet up and down. What happens? I generate electricity in that piece of wire. Well, the same thing happens
To the pipe.
to the pipe when I drop it in here like this.
Oh yeah, you
All
wrap
right,
it in.
and it's dropping down through there, and what it's doing is it's generating some electricity
Yeah.
in that copper tube.
Yeah.
All right, and when we have electricity running through a piece of metal, what happens?
It becomes almost like a magnet.
It may come, I have another magnet. So what's really happening is when I drop this in the top up here, and it starts to fall, it starts generating some electricity, which causes a magnetic field, which is in the opposite direction, and it's trying to push that magnet back up, slow it down.
Yeah.
When it slows down, of course, it doesn't generate as much electricity. The field gets slower. So it goes a little bit slower. What's all that got to do with my scale? You have any idea?
Balances out.
Generate electricity or magnet or something?
My scale's generating electricity?
I don't know.
Huh?
I think. No.
What did we start out with? We started out worrying about this
Mass.
thing bouncing up and down like that, all right? And we need a shock absorber on it.
Keeps it steady.
Okay. Let's take just a minute here. All right, let's move over to the scale again. All right, I have a paper clip.
Oh.
All right. My paper clip is not magnetized or anything, but let's just take a look here. If I put it in here, what happens to it?
It's stuck.
It's stuck.
And it's gonna rub against it when you.
Wait a minute. So there's a little magnet in there, right?
Mm-hmm.
Okay. And what happens? Watch when this moves up and down. What happens here? There's a piece of aluminum on this, all right,
So it's kind
that
of.
moves up and down between a couple magnets in there. So when that happens, what are we doing? We're generating some electricity in that piece of aluminum. And as soon as that electricity starts to flow through the aluminum, you said
It becomes a magnet.
it becomes a magnet, okay? Which is in the opposite direction of which way this is moving, right? So it dampens down. It's just like the shock absorber on your car, right? You go down the road, if your shocks are bad, you hit a bump, what happens? It goes boom, da-dum, da-dum,
Bounces up.
bounces up and down. If you've got good shocks, it may bounce once or twice, and then it stops. Same thing here. We have like a little electric shock absorber down here, right? On the
On the balance.
yeah. So as it starts to move, then
When it becomes attracted like down.
right. So now then, next time you're in the class, right, with Mr. Richards, and you get this out, ask him if this thing has any electricity involved with it. He'll probably throw you out of the room, but just pick on him a little bit. All right, so that's one kind of a scale. What about this one?
Electric scale or something?
Digital scale.
That's a digital scale, right? Runs off electricity. And we can turn it on. On the bottom of it, if we look down here real careful, there's a little switch where we can switch it between grams and ounces, right? Change the kind of scale we're reading, right? It's most of the science kinds of things we're going to use. We have a digital display here. I can turn it on, right? Press this by pressing the button. And as soon as we get it all settled down, it will settle out. What's it read?
17
17
grams.
grams.
17
grams.
grams.
Reading 17 grams.
6 something on top of it.
Okay.
0
there.
grams.
Yeah.
All right. 0. It's 0 now. We zeroed it out. Sometimes it gets a little stuck. You have to hit the switch again. Let's really test it. Okay. What's this weigh?
5 grams.
5 grams. It's a nickel, right? 5 cents, 5 grams.
It says 5 grams.
It says 5 grams.
Yeah.
Right. Sometimes if the batteries aren't very good in those, right? They've been used for a long time and the battery gets a little weak. It doesn't read exactly 5 grams, all right? But we put our nickel on there. If you have a nickel in your pocket, right, which sometimes I do, when my wife gives me a nickel for my lunch, then I can always test, make sure the batteries are good in it. Right? Now then, how does that one work? This one's the lever, right?
Yeah.
These work off the spring tension. How does that one work?
Some electricity.
Hmm?
Some electricity.
It's got electricity in it, that's for sure.
Yeah. If you put weight on it,
You put weight on it, but how does it know how much weight you put on it?
but it kind of measures the force.
Measure, okay, it somehow measures the force. Right. let me ask you a question. Right. Out here I have 495, okay? And it has 3 lanes of traffic, right? And I can get cars going down side by side down the 3 lanes of traffic, 50 mile an hour, and what happens? I get some number of cars to go past me, right? In a certain given time,
Yeah.
okay? If I take and I make that 3 lanes 2 lanes, what happens?
More
the
traffic.
cars, more
I
traffic.
get the slope's going to slow. I can't get as many cars going past me, right?
Yeah.
Right? So there's some opposition to cars going down the road. If I take the 2 lanes and I make it 1, what happens?
It'll be
Yeah.
crowded.
It'll be crowded,
Traffic.
and what's going to happen to the traffic?
It'll be like loud.
Nobody will be moving.
It's going to back up, right? Well, if it's 1 lane, they can move, all right?
But not
But if I make it less than 1 lane wide,
won't be
then they're not going to do anything, right? So the amount of traffic that I can get coming down 495 is dependent upon how many lanes wide it is. If I make it 6 lanes wide, what happens?
A lot of cars.
I can get a whole bunch of cars coming down, right? So electricity works basically the same way. Electricity is the flow of electrons, right, through a conductor, right? And that conductor is just like the highway. The wider it is, the more electrons can come through. The narrower it is, the less
Yes.
electrons, right? That's called resistance, right? If you have a lot of resistance, there'd be fewer electrons coming down the wire. If you had less resistance, there'd be more electrons coming down the wire. So if you take these 2 pieces of copper here, copper wire, hold that a minute, okay? You can have one too. All right, this is pretty wide, all right? This handles quite a bit of electrons, a little, right? They're little guys. So this handles quite a bit of
Yeah.
electricity, right? In fact, this is
Yes, it
standard
says-
house wiring, which
Yeah.
is like that.
It's
What about this one?
it's
thin.
It's thinner, right? So you're not going to be able to get as many electrons through this piece as you are through this piece, and with same amount of voltage on it. So this one has more resistance to the electrons flow than this one does, right?
Yep.
Got that?
Yeah.
The narrower the highway, the
Maybe
less
less
cars. The narrower
The wider.
the wire, the less
Less
electrons, the less current, more resistance. Balloon for you, Bernard, David, a balloon for you, and a balloon for me. Okay, hold it up like this. Everybody's laughing at us right now, right?
Yeah.
That's the fun part of this science thing, because we get to have people laugh at us. We're just like Jay Leno. We can be comics if we want. All right, it's a certain width.
Yep.
Right? What if I were to take it, both hands like this, and stretch it? What happens to the width?
It becomes
It's
smaller.
longer.
It gets smaller, right? So if this were my highway or my piece of wire, right, like this, I get a lot of cars going up and down it, all right, a lot of electrons running through it, and if I stretch it a little bit like this, it gets narrower, and the more I stretch it, the more force I put to it, the narrower it gets. So what happens to,
The cars become like all in
Yeah.
line.
they become all like in line, and there's more resistance to the cars. If it was electricity,
The
and the wire
electrons-
was getting smaller like this, and smaller and smaller and smaller,
The electrons will be all.
Yeah.
there'd be more
Yeah.
resistance, right? It'd be more electrons. No. Put the balloon down. We don't need to play with the balloons anymore. Take your wire. Take this piece of wire, right? And you go like this. You pull on it. Guess what happens?
It's not stretching.
Guess what's happening to it? What do you think's happening to it as you pull on it?
It's not stretching.
The same thing is happening to that piece of wire when you pull on it like that. It's happening to this balloon.
It's stretching.
It's stretching. Not very much. A little bit. It's stretching just a little bit. And what's going to happen when it stretches?
The
It gets
electrons,
narrower.
Yeah.
And as it gets narrower, what's going to happen to the
Less
number of electrons that can get through it?
A little resistance.
Less
There's more resistance, right?
And less.
And less electrons. Now, we can measure that. Right? With some electronic circuitry, we can measure how much the resistance to this piece of wire changes as you go like this. Right? And especially if this were a real long piece of wire and a real thin piece of wire, like maybe if we took this piece or something even thinner than this, and made it 20 feet long, and you both of these, you got on the end of it and pulled it, okay, you could change the resistance quite a bit, and we could really measure it. That's what we do inside that. That's how that scale reads. We have a thing called a load cell, right? And what it is a piece of plastic with some wire, right, like this, right, etched on the piece of plastic. And if I were to take this piece of plastic like this, and there's some little wire connections coming off here, these little conductors going off into electronics. And if I were to take this piece of plastic and I go like this, what's going to happen? I'm going to stretch each one of these. What happens to them when I stretch them? They're going to get narrow.
Yeah.
So what's going to happen to the resistance going through?
They're making
More
more
resistance.
There's going to be more resistance. So if I were to take this little load cell and I were to go on it, right, I get more resistance, right? If I were to, so basically the same thing happens in there, right, on that electronic scale, that digital scale. When you put some weight on the tray on top of it, right, there's a little load cell down inside with all these little wires in here like this, and it's causing them to stretch apart and change the resistance. And then these wires hook up to the electronics, which measures that resistance and gives you the display over there. The more weight we put on the tray,
The more
the
resistance.
more resistance we're going to have, and
the more
the bigger, the higher the reading, right? And it's very, very accurate, right? Or it can be very accurate. That particular scale there is not really all that accurate. Now, we can use it to measure just a few grams like we do with that scale.
Yeah,
or-
what if you put too much?
Oh, well, if you put too much,
Yeah. It'll go
same
off.
thing happens if you put too much on that one. It happens to this one when you stretch this one too far.
If it
Because what
comes-
you're going to do is you're going to pull the load cell
So
apart,
much.
right? And then
Oh,
you
so it
throw it
works-
away.
It works almost the same way as this one.
Sort of, yeah, right. Now, these load cells, or strain gauges, as they sometimes call them,
Yeah.
one of the things they could do is, all the bridges where the big
Pipes.
pipes and the, what do I want to call them? The pillars are holding the bridge up,
Yeah.
right?
Electronic plastic.
Well, what they can do is they can take a whole bunch of these load cells, paste them up to all those things that are holding the bridge up, all those supports on the bridge, and they can actually weigh the bridge. And they can weigh the traffic that goes across the bridge.
They could measure how much weight could go on the.
Yeah, how much weight is on the bridge? How much snowfall? If they need to measure it, they can actually measure. The big trucks, the big tractor trailers.
Yeah.
In a lot of states, they weigh them, right?
Yeah,
Make sure
so
they're not
that's-
overweight.
You
Right?
have to
If
pass
drive-
through.
Hmm?
Yeah.
There's a scale along the side of the road. Well, those scales, back when I was your age, okay, were all this kind of a scale. Right? They were all mechanical kinds of scales, like the triple beam balance. Today, guess what they are?
This one.
They're like that digital. They're all
They're
electronic
digital.
scales, like that digital scale, and they have load cells. They have several of them actually, because that truck is pretty long, right? And it weighs a lot, so they have those on the scale. So when the guy drives up on there, what he's doing is he takes the little load cells and he goes. The weight of the truck is pulling them apart, making the wire in the load cell a little bit narrower, increasing the resistance, which we can measure. All right. So, now, what are we going to do next? Got a suggestion?
It's a calculator.
Well, I brought the calculator in case we needed to calculate something. We have to do it, okay? What if we didn't have all this? And you wanted to weigh something?
My hands.
Hmm?
They're like hand or something.
You want to guess? You want
Like
to you want to guess between this
yeah, it kind of goes
and
down.
this, huh? A quarter and a nickel.
Yeah.
And you're gonna say which one's heavier?
Yeah. If it's too heavy, you just. Oh man, sorry, but
All right. I mean, let's do a trick, okay? You got a nickel? Put your nickel in that hand. Keep it in your hand. Close your eyes. right? Which one's heavier? Don't count the pennies.
Kind of the same.
They're kind of the same, huh? All right, you counted the pennies, all right? Because I put a nickel and two pennies. The nickel is 5 grams. The 2 pennies are also 5 grams. But it's a little hard to tell, right? If you couldn't count. Okay. So maybe that's not too good of an idea.
Yeah.
So what we want to do, if we were at home and we wanted to weigh something, we didn't have a scale.
How about like make one of your own?
Make one of your own. How you gonna do that?
Take take a level and like
Get
Okay, you could take a lever and
around and
Make
a
one?
fulcrum and
Yeah.
support it.
okay, you could do all that. But you could also do this. A piece of cardboard, paper clip, nice pretty red string, right? A little baggie, and that's my scale.
And how much would you know?
You put the thing you want to weigh in the bag,
Yeah?
and then
You hang it on a
pulls
spring
it
or
down.
something?
Well, let's watch it a minute, okay?
I think
If we pull down on this string, what happens?
the board
It'll go down. Right?
tilting to the side.
Oh,
The board.
now I get it.
It was your idea, all right? You were going to take a lever and a piece of wood and build a fulcrum and all that sort of thing. I have a same thing here, all right? Here's this paper clip is acting as the fulcrum.
Fulcrum.
All right, I have a lever here, right? I also have a load, which is this piece of cardboard. I tied a piece of string on it, and with my little baggie, because if I want to take my little baggie and I want to put the quarter in the baggie.
You know.
All right? And the string is there. When I put a quarter in it, what happens? It's going to pull down on it a little bit. All right? We got one
Tilted to the
quarter,
side.
Yeah, it's
and it's going to move to the side, right? So what I need to do then, I need to calibrate my scale. So I take a little marker, and I put a mark.
Yeah.
All right? Now, if we're
Sorry.
real careful, hold on to the marker, because we don't want to measure just 1/4. We want 2/4. All right? Wherever it is it, you can't hold on to that
Okay,
part.
sorry.
You look like the butcher putting his thumb on the scale and make a weigh.
Right there.
Okay? So there's another one. We take another quarter and put it in, and we can calibrate it. We could actually, instead of using quarters, we could use nickels, which is a little bit more.
Hold on, sorry about that.
He's writing on me, Bernard. Maybe I should have had you do this.
Yeah.
Okay, so now then, so we could we keep adding weight, we could calibrate it. Now then, we come along with something we didn't know what the weights were, and we could also label them, right, whatever each one of those are.
Like
Quarter.
1/4, 2/4.
Yeah, 1/4, 2/4, and we know quarters weigh
Um,
5.68, what is it,
yeah,
5.68?
5.67.
All right, 5.67 grams. So then we can build our own little scale.
Yeah.
Right?
We
So-
compare it to other weight too, if we put the same thing on the other side.
Yeah.
How about if you put like another magnet in here? Whoa,
What?
that's a strong magnet.
Yeah, it's a strong magnet, right? What do you want to do? You want to put the magnet in here? You want to put the whole thing in here? Put it in there.
It could go off scale, can it?
It may go off scale, but put it in there.
Ooh, yeah.
Right? It'd be way up here, and we could mark. If we knew what that weighed, we could mark it, and we could calibrate it with that.
Yeah.
Or you could start out with pennies, right? Put 1 penny, 2 pennies, 3 pennies, 4 pennies, right? And you could get up as many pennies as you want, and we have our own little scale. Okay. So now, what have we got? We had that blue lever arm. Let's get it back for a moment. Let's put it over here. All right, so that's like a lever. We got a fulcrum, and what we're doing is, since the two lever arms are equal, all right, we have to put our weights in the center here where the axes are, and then we balance it up. And if we know what one of them is, we know what the other one is.
Not like this one.
Yeah. So this one does what?
It's
Measures.
It works the same way, right? It's a lever, right? What about these two?
This is a spring.
These are springs, right? Spring scales. Right, and that one over there, that's a
Triple
digital
digital.
scale, but it
It
uses
uses
that load cell that we
scale.
were talking about, right, which is actually the stretching of
Wide.
a little wire, right? Now, and what makes this thing work?
The
Gravity, right?
Yeah.
Gravity pulling down on it, right? Causing you to have weight. Is the gravity the same everywhere?
No.
Yeah. No, not.
No.
No.
No, it's not the same everywhere. It's not even the same everywhere on Earth, right? Because the amount of gravity that we have right here is dependent upon how far we are from the center of the Earth, right? And if we go up to the North Pole, we know the Earth's squashed just a little bit, right? And the gravity at the North Pole is going to be a little bit different. What about if we went to the moon?
It'll be 1/6.
Less gravity.
There's less gravity. It's about what'd you say?
1/6.
About
of the-
1/6 of
of
it.
the
So if you weighed 120 pounds here on Earth,
yeah, right.
you went to the moon,
It's 20 pounds. No.
yeah, 6
20.
into 120 would be 20 pounds, right?
Yeah.
But that all depends on what you weigh it with. If we were to go to the moon and we were to tie your little feet together, right, with one of these spring scales and hang you on here, right, on Earth you weigh 120 pounds. The moon, right, because what you're doing is
Yes,
gravity's pulling down on the weight and stretching the spring. We go to the moon, whereas gravity's only 1/6, you would weigh 20 pounds with this spring scale. Okay? But, and also this one. But if we go to the moon with this scale, all right, or first on Earth we set you here, and you weighed 120 pounds here. We put 120 pounds here, it balances up, right? So we take you and this 120 pound weight we have, along with that scale, and we go to the moon and we set it down on the moon.
It'll become 1/6 of everything, the 120 pound and the.
Yeah, everything will become 1/6. And what's going to happen to the scale? It's going to stay balanced, right?
Yeah.
What about that one?
It's gonna balance out. It's gonna become 1/6 of everything.
It's going to
Yeah.
become 1/6 of everything. And if
This
you,
is gonna weigh 1/6.
if you were to have a big triple beam balance where you could read 120 pounds, right? It would still read 120 pounds on the moon, right? What about that one over there?
The
This
same.
one, this no, yeah, I think.
All right, what we're doing is basically,
This
and
one
that
will
one, the
change.
sensor, it would change, right? Why?
Because the stretching, it'll be.
The stretching would be dependent upon how much gravity is
5,
pulling down
yeah.
on it. So when you were here on Earth, you'd have 120 pounds of force pulling, stretching it. If you went to the moon,
You had 20 pounds.
you'd only have 20 pounds force stretching it. So this triple beam balance and this little simple lever, right, would measure the same here on Earth or whether you were on the moon. So sometimes these are referred to as mass scales, right? Because they read the same no matter what the gravity is, right?
Yeah.
The weight, you may have heard somebody talking about that in the classroom this morning when they were talking about mass. Somebody was
yeah,
looking.
the weight of a sun.
Yeah.
or
Okay.
something.
What's the
Yeah.
difference? What's the difference between weight and mass?
In mass.
Mass.
Weight, right? The weight is the gravity.
Pulling on.
Yeah, it's
Yeah.
the force that gravity's pulling down on you.
Mass.
So if you go from the Earth to the moon, the weight's going to
It's
change, right?
But the mass is
But the mass is,
It's-
you can think of it as how much material you have,
yeah, inside.
right? So if we take you to the moon,
I won't
and
change.
assuming you didn't explode up there and to low gravity or low vacuum,
I won't
right?
change.
You don't change. You still have the same mass, right?
Yeah.
So you got the same mass whether you're on Earth or whether you're on the moon or whether you're in outer space or wherever you are. So that's why they refer to this one and this one as mass scales, because they weigh the same no matter where we are. Because what you're doing is you're relying on gravity to balance it up. All right, so now then, when you go back into the classroom and you have to weigh things, you have a little bit better idea of what
Yeah, what you're doing.
what it's doing, right?
Yeah.
And if you take this,
Don't stretch it like that.
don't stretch it, right? And that one over there,
This one, don't put too much weight on it.
don't put too much weight on it. And this one here, to keep it from bouncing up and down like that,
Yeah,
what do
have
we
a
do?
magnet.
right here.
Well, we can adjust it. Okay, this
Yeah.
is the
Yeah,
adjustment for the
and
make it
use a
zero.
magnet.
And we have a magnet.
They have a little magnet in there, and that piece of aluminum starts moving up and down. It's going to generate some electricity, which generates another magnetic force and cancels out the magnets that are in it. So it dampens it out, just like the shock absorber in the car. So that's it for today, and we hope you all understand how to weigh things now. Okay, so we're